Hello everyone, welcome to this video. Today we are going to talk about BLDC motor dynamics, and this is the outline of this presentation today. First we will see the BLDC motor equations, then we will present the dynamic model of the motor. From this dynamic model we will obtain the different transfer functions of interest for the BLDC motor. And also, as usual, we will be showing several LTspice simulations to illustrate the different ideas and concepts. This is the fourth video in this series. Previously, we have seen in videos number 15 and number 16 how to create a BLDC motor model and how to drive the motor. In the video number 17, we have seen how to implement PWM control to control the speed and the torque of the motor. So let's see in this video how we can obtain the dynamics of the BLDC motor. As we have seen in previous videos, here we have the electrical circuit of our BLDC motor. Here on the right we have the back EMF voltage waveforms in red and the line back EMF voltage waveforms in blue. And also we have seen that in order to operate the motor, what we are doing is to apply a DC voltage that we are going to call here VD between the different phases of the motor. For example, in a first interval here we are applying the DC voltage between phase A and phase B. So we are going to have a current I circulating like this. And of course, it's very easy in this circuit to obtain this differential equation here in order to obtain the behavior of this current that is circulating through the windings. We know also that during other intervals we are going to apply voltage between the other phases, phase B and phase C, and phase A and phase C, and so on. So we can imagine that at any moment we are going to have a current like this, that it is going to follow this expression, this differential equation. So we are defining here the equivalent resistance, which is twice the resistance of one phase. Then we have here also the equivalent inductance, or effective inductance, that we have here is twice this value here, the self-inductance minus the mutual inductance between windings. And then also we know that the line back EMF EAB is equal to twice the back EMF EA here. And the amplitude, as we have seen in previous video, the amplitude here of this one and the amplitude here of this other one is proportional to the speed of the motor. So in the case of EAB is twice the constant, proportionality constant kV times the angular speed of the motor. So finally we get this first differential equation that we can use to model our motor. A second equation that we need to model the motor is related to the electromagnetic torque TE, which is equal to the electromagnetic power divided by the angular speed, and can be obtained using this expression here. At the end, the electromagnetic power is the power that is going to be absorbed by these voltage sources here, by the back EMF voltage sources. And the trick here to simplify this expression is the following. First, we know that the back EMFs EA, EB, and EC are going to be proportional to the angular speed. So because they are in the numerator and we have the angular speed in the denominator, they are going to compensate each other, both effects. And the second one is that we don't have simultaneously current through the three windings. We only have current circulating like this during one interval, and we don't have current here during this interval. In another interval we have current through these two windings, but we don't have current on the other. So because of this, it is possible to say that the electromagnetic torque TE is going to be approximately proportional to the current I that we are imagining that is circulating always through the windings. The constant KT is the torque constant that we can obtain from the characteristics of the motor. So in order to better understand this, we are going to make an LTspice simulation to obtain this characteristic. So here we have our LTspice circuit as usual, as we have seen before. What we are going to do is several simulations with different values of the load torque. Here we have this list of values. We have done similar thing in previous videos. We are going to simulate up to a steady state operation and saving data at the end for the last 10 milliseconds. And then we will process all the results in order to obtain the average value of the angular speed, and the average value of the torque, the RMS value of the torque, and the RMS value of the current through phase A. We are going to use the RMS value of the torque. It's going to be similar to the average value, but in order to be more accurate, we are using in both values, the torque and the current, the RMS value. So now we can run the simulation. It has to perform, as we can see here at the bottom, a total of 8 simulations. So it's going to take a little while. Meanwhile, we can take a look, for example, at the angular speed to see that everything goes well. We can even add another pane and take a look at the electromagnetic torque. Here we can see it, and so on. Maybe we can add another pane and see the current through phase A. So here are the different values of the current for the different values of the load torque. So now the simulation is finished and we can represent the results. For this, as usual, we press Ctrl L on the keyboard and then we can see the different values of the speed and the torque and the current, but it is better to do a representation. So right click on the mouse and select plotting. Here we are going to select for the horizontal axis the current IA RMS, and then we are going to represent the torque at another trace and represent the RMS value of the torque. So we can see that we have this linear behavior, is perfectly linear. We are going to analyze this better, and we can do measurements using the cursor and so on. Here we are analyzing this characteristic obtained from the simulation. So here we have the torque as a function of the current, and here on the right on this table we have represented for different points of torque and current, and we have calculated the ratio between torque and current, and in order to obtain this constant KT. So we can see that they are all very similar values. So this means that this is a line that goes through the origin, and this is the constant that relates torque and current. So we can get this value at the end approximately for the constant KT, which is 23.5 10 to minus third exponent newtons time meter per ampere. So as you can see, it's also very easy to obtain this constant from the characteristic of the motor. We only have to go to the datasheet and look for one point giving the torque for a given value of the current through the phases, and then we can get the constant from this information. So now we have everything to obtain the dynamic model of the motor. We have the first differential equation that we have seen, the second equation that relates the electromagnetic torque and the current I, and then we need also this other differential equation that we have seen previously, which relates the torques, the angular acceleration, and the angular speed. Remembering that TO here is the no-load torque, and because we are assuming that this is a constant value, it's not going to take any effect in the dynamic behavior. So then we can take the Laplace transform of these differential equations, and then we will obtain these expressions here directly, from which we can obtain the complete dynamic behavior of the motor. So summing up, we have here the equations that we need to model our motor with all the variables in the S domain. So these variables represent a small signal changes in the different variables, as we know. And then here is the representation of the behavior of the motor. So we can distinguish mainly two transfer functions. We have transfer function GC, which we can consider the control transfer function. The input is the voltage VD, and it is going to affect to the angular speed of the motor. And also we can obtain another important transfer function that we can consider as a perturbation, which is this transfer function GL, in which we have as input the load torque, and it is going to generate also a perturbation on the speed. So with these two transfer functions, we have a pretty good model for the dynamic behavior of our motor. To obtain these two transfer functions is a matter of operating on these equations that we have seen. In the case of the transfer function GC, in this case, we want to obtain how it's going to change the angular speed when we have a change in the DC voltage that we are applying to the motor. So in this case, we are going to make null the perturbations on the load torque. So this variable here, T load, is going to be 0. So we put here 0, and then we solve this system of equations. So we obtain here the current I, we obtain the voltage VD, and then solving we finally obtain this transfer function here. And as we can see, it has a characteristic polynomial here, which is a second order polynomial. To better understand the dynamic behavior of the motor, we can study this transfer function as the typical second order transfer function, as we are showing here in this expression in red. So from the previous expression, we can obtain the DC gain in GCO, which will be this expression here, the natural frequency, and the damping ratio of the system. So with these expressions here, we can do the representation, and it will be as shown here on the right. We will have a second order system with the DC gain, the cathode frequency given by the natural frequency of the system, and of course we will have some kind of second order response depending on the value of the damping ratio. In the same way, we can obtain the perturbation transfer function GL which gives how the angular speed is going to change when we have a change in the low torque. So in this case, we are making VD, the perturbations on the DC voltage, equal to 0. So here is going to have 0, and then we have the system. In a similar way, we solve the system, and then we obtain this transfer function. Of course, we are going to have the same denominator, the same characteristic polynomial as in the previous transfer function, but in this case we have a 0 here in the numerator. And also we have this minus sign here because, of course, in the DC operation, when we substitute s equal to 0, the gain is going to be negative, because when we increase the low torque, the angular speed has to decrease. Now we are going to obtain the dynamic behavior for the motor that we have been using in these presentations, in these videos. Here we have our model with these parameters here, and then we can obtain also all these values that we have seen along this presentation. The equivalent resistance, the equivalent inductance, the moment of inertia is this value here, the viscous friction coefficient, which is this value here for the motor in this parameter here. We have Kv, also is another parameter of the motor, and then we have Kt, which is the parameter that we have just obtained in this case by simulation. And then as summary, here we have both transfer functions that we are going to calculate. To do the representations, we can use WinPython as usual. There is a video, WinPython number 3, that shows how to do frequency analysis and body plots. So if you are not sure how to do this with WinPython, please take a look at this video here. And then we have here the different information, the different parameters, the both transfer functions, GC and GL, and then with these commands here we can do the plottings, and by changing here this value of the different iterations, we can print different values also of the different of the curves very quickly. For example, here is for the first iteration for I equal to 0. Note that this is not a current, it's just an index for the iterations. So in this case, and this is for a frequency of 9.9 Hertz, so it's 10 Hertz, is this point here, in order to obtain the DC gain of the characteristics, so it's 33.8 for GC and 50.4 dB for GL. Also, we can obtain the cutoff frequency if we go to the point in the phase representation here at which we get minus 90 degrees, and this corresponds to a frequency Fc approximately equal to 638 Hz. So now what we are going to do is a couple of simulations in LTspice in order to obtain also these body plots by simulation, in order to confirm that both the theoretical analysis and the simulation are in good agreement. This is the circuit to obtain the control transfer function of our system. Here what we are doing is to inject a signal here superposed with the DC voltage at the input of our converter, and then the output is going to be the angular speed of the motor here in radians per second. And then we are going to do several simulations at different frequencies of the signal that we are injecting here, of the perturbation from 150 Hz up to 10 kHz, and with 10 points per decade. And with all these statements here, we are going to process the data, and then we will be able to represent the body plot of our transfer function. We have seen how to do this in this previous video, LTspice number 6, open loop frequency response of a DC-DC converter, which is similar to what we are doing here. So if you are not sure about this process, please take a look at this video, LTspice number 6. And now we can run the simulation. It's going to take a while because we have to perform a total of 20 simulations, as we can see here at the bottom. So I will be back when the simulation is finished. So now the results are ready, so we can see, for example, the speed here at the different frequencies. But what we are interested in is in representing the body plot, so we can see the log file pressing Ctrl L, and here we have the different perturbations, frequencies, and then the different results in data. We can see the different values, but it is better to represent this graphically, so we can right click on the mouse, plotting, and then we say yes here to combine the data, and then here we can right click again at trace and select gain, and here we can see the in solid line we can see the gain of our transfer function, and in this continuous line here we can see the phase of the transfer function. We can check some values and see that they are very similar to the theoretical ones that we have obtained. Here the gain in dBs is 32.5 dBs, very similar to the theoretical value. And then if we go to the point, for example, in which we are going to have minus 90 degrees, we can get a frequency that is something similar, also is 618.7 Hertz. So we can see that the results are quite similar. And now we can do similar process to obtain the perturbation transfer function. In this case, what we are doing is to introduce here the perturbation on the load torque using this sinusoidal voltage source here, and then we will also get the corresponding angular speed at this point here. And also, as we have seen, by processing all the data corresponding to the output, which is the speed, and the input, which is the signal that we are injecting here on the torque, then we can obtain the gain and the phase of the transfer function. In this case, I had to add this series resistance here to improve the convergence of the simulation, but it's not going to have any important effect on the results. So now we can run the simulation. Again, we are going to have a total of 21 simulations, so it's going to take a while. So I will be back when the simulation is ready. Now we have the results, so we can see the speed in time just to check that everything is okay. And now we can, as usual, press Ctrl L and check that we have here the different frequencies of the perturbation and all the data that has been properly obtained. So now we can do right click and plotting, yes, and we can add a trace with the gain and phase. So again we can see that we have a second order response. We can measure the DC gain of the perturbation transfer function, which is 53.9 dBs, so it's very similar to the value that we have calculated theoretically. And we can check other values and see that they are also in quite good agreement. So with this, we conclude our presentation today. Thank you very much for watching. Please let me know if you have any comment or question about the content of this video. I hope it is useful for you, and I hope to see you in the next video. Goodbye now.